Welcome to a new video about DC series motors. It will be our example number 2. In this example we will again look at interesting problems. So we have a DC series motor and we have a specification of 480 volts and 90 kilowatts. And this DC series motor has also a field resistance of 100 milliohms and an armature resistance of 20 milliohms. In addition, we have for the full load condition a terminal current of 180 amps and also the shaft speed in this condition of 600 RPM. Okay, what are the required calculations? We have here the required calculations. Calculate the back EMF, the developed power, and also the developed torque, and then finally also the efficiency of this motor. Okay, let's look at our solutions. And again, we start with a model, and this is our model as we have discussed also in the previous example for a DC series motor. You can see the terminals where you apply the DC voltage. This is the part of the field, and this is the part of the armature. And this is the back EMF where it's also connected to the shaft, which will then rotate. Okay, now in addition, we of course have a series configuration. It means the terminal current will be then equal to the field current, will be then also equal to the armature current. So that is actually a nice condition we can use later on. In addition, what this actually meant by this 480 volts and also 90 kilowatts, that means actually the following. This representation means that your terminal voltage will be 480 volts and your input power will be then 90 kilowatts. That's actually the meaning using this format. So let's then look at question A, back EMF. Now, back EMF is actually in this loop. Again, we can use then the voltage loop, Kirchhoff voltage law. So we can set up again this equation. You can see this voltage, VT, terminal voltage, is applied to these 5 elements, the RF, LF, RA, LA, and also the back EMF that's actually shown here. And again, we have a DC voltage applied. That means there will be a DC current in it. That will also make the reactances of these two inductors 0. So we can say this will be 0 and that will be 0. So this will be actually simplified in this form. Now we have the back EMF here, and now we also know the required values from our information in this example. Now we already said the terminal current is equal to the field current and also equal to the armature current. So we can just say armature current here is also the terminal current. You can see that also the RF and also RA are taken together because the field current is also equal to the armature current. So this is this equation we can use. If you now substitute the values given here in this exercise, you can see this is then the armature resistance, the field, and also we have the current for this condition. Now, finally, we can then calculate what the back EMF must be. Will be then 485.58 volts. Okay, that's for the back EMF. Going to the question B, which is then developed power. Developed power is given by the back EMF times the armature current, or the terminal current in this case, it doesn't matter. Also in the series combination. Now we have now the necessary information. We can say 458 times the 180 amperes. That will then result in this power. So it is then 82,440 watts. That's what we have for our developed power. Now moving on to the developed torque. Developed torque is related to the developed power using this formula. So developed torque is equal to the developed power over the rotation speed for this condition. Now we have already the rotation speed, the shaft speed, which is given in the RPM. So the units are in RPM. So we need to convert that to radians per second. That is done just using this formula. So you substitute here in 600 and 2 pi over 60 or pi over 30, what you prefer. And then you have 62.8 radians per second. Now, if you now substitute it in here for the developed torque formula, using the value we have calculated in B and also this for the omega m, then you will get 1313 Newton meters. That's for question C. Finally, the efficiency. Efficiency is always defined as the output power divided by the input power. So how much power do you deliver actually to the rotation? Now the output power is actually also the developed power, and developed power is already calculated, which is actually going to the shaft in this case. That means this is then the developed power, which is then again 82,440 watts. The input power we know from the specifications of this series motor, that is 90 kilowatts or 90,000 watts. Now we can then use these two values in here in the formula of the efficiency. Just substitute the values. You will get a value of 0.916 or 91.6% for our efficiency, and that will conclude this example. Alright, again, if you have any questions, please let me know and I will try to answer them as soon as possible. See you next time. Take care.